our quad rotor here.
It's a quadrocopter, so it's got 4
We're going to put this
propellers.
inside of our rocket up there.
We decided to use it as opposed to the regular helicopter because regular helicopters, although they may seem simplistic, they got 1 propeller. It's not because you have to pitch the propeller. So we used 4. So basically, these 2 control the, angle, pitch, roll, and then yaw. Okay. So what we're doing this year is we're putting this helicopter inside this rocket. So this top cone part. Okay. So upon apogee, once we launch the rocket 1 mile up, there's going to be a controlled explosion down the middle. And it'll separate the rocket, and then this is going to pop out. It's going to be folded up. We're going to make a foldable design. And it's going to be taking measurements, panoramic view, photography, video imaging, etc. Just the usual, Like nothing too revolutionary when it comes to measurements, but this is the first one of its kind. MIT tried a project last year. They failed, so we're going to try one up them this year and put a flying object into a rocket. So yeah.
How high was that?
This one, well, the rocket is rated for, it could go pretty high, 10 miles, depending on what size engine you put in. Specifically, this competition, USLA is 1 mile up, and then once at 1 mile, it's got to stop. Because the closer you get to 1 mile, the better you get points, So yeah. So we got basically 2 teams, 1 for rocket, 1 for quad rotor, and we're hoping to. Quad rotor is in its beginning stages right now. I've worked on it for a couple of years, but I'm trying to speed everyone up else in the club because there's a lot of stuff that goes into it, electrical, mechanical, programming, and we're going to get everyone up to speed on it.
So does it fly back down to the ground afterwards? Or?
Yes. Once it goes to apogee, it's going to be hovering there for a couple minutes. The max speed of this quad rotor is 40 miles an hour, which is pretty fast. The propellers rotate at 12,000 RPM, but it will basically hover back down to the ground to your position. It's going to be GPS, all control system, controlled. So, yeah. Any questions?
How tall is this rocket?
It's 11 foot. We have to take the tiling out. I wouldn't fit. But yeah, it's 11-foot rocket. Engine probably goes up to here. Right there. It uses NASA grade fuel, like the same fuel they use on the space shuttle, but in very low quantities. We use 1 kilogram, 2 kilograms as opposed to 10,000 kilograms. I think it's called ammonium perchlorate. I'm not too sure actually, but we use their fuel, and it flies. Like here, if you guys can watch the. It's actually horizontal, but it's gonna launch that one.
Actually, it's ammonium perchlorate.
Yeah.
Yeah, it's ammonium perchlorate,
All right, nice.
APCP. Ammonium perchlorate composite propellant. So that's the rocket launch that we launched right outside here. That's in Flatsville, Illinois. We launched with CIA, which is Central Illinois Aerospace. They launch a bunch of rockets during the year, and they get the proper FAA clearance and proper notification to like airplanes and things so that airplanes don't fly above so we don't hit them. Also, one of the things that we had to deal with on that launch were skydivers. Actually, there were skydivers in the distance, and you have to make sure that all the skydivers are on the ground so you don't hit them, too. I'm sure that'd be terrifying on their end to see rockets flying up. But yeah, this is the rocket that we built for the NASA University Student Launch Initiative last year. This rocket went exactly 1 mile up as it was designed to do. It went 98% of a mile, and we were in the top 5 schools to do that. It carried a scientific payload on board that measured temperature, pressure, humidity, solar radiation, UV radiation, and it also had a camera, which is why we installed this window here. The camera was actually attached to a couple servos, which are like motors that actuate really easily, or really small intervals, and a gyroscope. So it measured rotational data from the actual rocket, and then rotated the camera so it always stayed horizontally during the descent. So we'd get a horizontal video. Unfortunately, we didn't get the video from it because what happened was this rocket, the way it's designed is it's so large and it launches so high that we actually have to put 2 parachutes in it. We put a main parachute, which goes at the top, and then what's called a drogue. And the drogue goes in the bottom down here, and the drogue deploys at apogee. Apogee is the height at which the rocket reaches its pinnacle, so it's the top part. And the reason you want to deploy the main parachute up there is because for this rocket, that was 1 mile up. For other rockets, that could be 2 to 5 to 10 miles up. And if you deploy a parachute up there, your main parachute, the winds will blow it for miles. You could lose your rocket very easily. And a rocket like this might cost $15,000 to $2,000, and you don't want to lose that. So we deploy a small parachute above that just slows it to an acceptable amount of feet per second, and then we deploy the main parachute about 700 feet above the ground from there. Problem was, on that launch in Huntsville, Alabama, where we launched it, the main parachute got tangled and did not come out. And so it actually hit the ground at 30 feet per second. Memory card popped out of the slot and we didn't get any data. But this rocket is built out of fiberglass, which you can feel here. This is fiberglass. This is a coupler that goes inside of this other rocket that we're building. It's extremely lightweight. It's a spun, wound material that's covered with resin, and it's extremely strong. Did you want to feel it? You can pass it around if you want. This material fell from 1 mile, and the only crack that you can see is right there. It's really impressive. There were some cracks on the fins too, but at 30 feet per second, that's the only damage that happened to the rocket. So it really speaks to the robustness of that material. During our test launches, we were actually launching over 1 mile, and there's a lot of math that goes into weighting the rocket properly and talking about and figuring out how much propellant to put inside, what size motor, etc. And so what we actually did was, since we were shooting about 600 feet over the goal of 1 mile for the competition, we had to make this giant slug, is what we called it, a slug of buckshot. And this is resin, like epoxy. And we glued this in right at the center of gravity right there. We just drilled it in. And that made it so that this rocket would not, the aerodynamics of it would not change, but the actual, yeah, you're fine. The actual weight was weighed down so it didn't go as high. This here is an antenna. It's a directional antenna, so what you have to do is have a really good eye. And when the rocket's launching, you point it at the antenna and you carry it all the way up. And there are different devices, like I was saying, the different atmospheric sensors on there, as well as these are called altimeters. They measure the altitude. They record the data from the launch. They measure altitude data, they measure gyroscope data, or sorry, not gyroscope, GPS data and acceleration data. And so this antenna, we connected to our computer, and it would tell us live where exactly our rocket was. And we could actually plot it on Google Maps if we wanted, the entire trajectory of the rocket as it was happening in real time. You guys saw the launch video. This is another rocket that we're building right now. This is for another competition. And as I was saying, that rocket was built to go exactly 1 mile and carry a scientific payload. This rocket, which actually I just put the nose cone on there for looks, this rocket will be 7 feet tall when it's completed. This section's part of it too. This rocket is designed to go 3,000 feet exactly and carry a video camera that will transmit live data on the way up. Every engineering project that you do has requirements or like a goal that you want to accomplish, and then from there you determine what kind of equipment, what kind of fuel, weight, whatever your project is that you need to develop to meet that goal, meet all of the requirements. So this one, since it only needs to go 3,000 feet, we need a smaller engine. This is a J. If you've ever used the smaller rocket engines like A, B, and C, they double in size each time. This one's a J, this launched on a K. We decided what kind of rocket motor we needed. We decided what kind of material, we went with fiberglass again, and what the weight was and different requirements like that, based upon the fact that we needed to put a video camera inside and reach 3,000 feet. So that's pretty much it for rockets. I don't know if you guys have any questions on that. After that, I can go to this iPad thing. No? Okay.